Professor Yasuhiro Kato. They worked together in the group, and their pioneer work was very, very important to shift the search of critical materials, rare earth, from land to the ocean, okay, to the deep sea ocean. And that will be the issue of this day at SHIFT. We have explored application in biomedicine and energy, but all of these applications work with some critical elements, these critical materials. And today, SHIFT will be principal devoted to these critical materials, all this plenary session and also this afternoon, especially this afternoon. We will have a roundtable with experts from United States, Tom Lograsso from United Kingdom, Frances Wall, also from Japan with Professor Kentaro Nakamura, and from Madrid, and from the European Union, Pierluigi Franceschini and Roland Gauss. We'll have a very, I think, quite interesting roundtable to participate with the audience, with public, and with all of you to debate this. What are critical materials? Why are they so important? Where can we find them? So I will give the floor to my colleague, Professor Nakamura, and he will address the audience about this rare earth-rich mud as a new source, as a potential source of critical materials. Please give a warm welcome to Professor. Thank you.
Good morning, everyone. It is a great honor to be here today, and I'd like to thank Jorge for invitation and kindly introducing me. Today, I'd like to talk about rich mud, new mineral resource for rare earth elements from deep seabed. In recent years, the global environmental problems, including the climate change, have begun to become the most urgent issue for our human society. And the United Nations started to tackling this problem. Yeah, so recent days, many countries have begun to promote the electrification of vehicles and rapid growth of renewable energy, including the wind power generation. And the key technologies for these tendencies heavily rely on some special elements called rare earth elements. And the rare earth resources were very highlighted in 2019 because of the trade conflict between China and the United States. And also it reminded us the global rare earth crisis in 2010. So these clearly demonstrate that the rare earth elements resource is a critical issue for the world economics and politics. Because China is by far the largest supplier of the rare earth elements, other countries, including the United States, Japan, and also EU, totally depend on the Chinese resource. And the US and the EU are now seeking a way to strengthen its supply chain by getting rare earths from sources other than China. But it's not successful at this time. And here I would like to introduce the new rare earth element resource from the seabed. So, first of all, I'd like to introduce rare earth elements, REE. The rare earth elements are generally referred to 15 lanthanide elements plus yttrium. And Scandium is sometimes included in the rare earth group. And rare earth elements are commonly divided into two groups of the light rare earth elements, LRE, having a lighter mass number, and the heavy rare earth elements, HREE. And heavy rare earth elements, including the dysprosium, terbium, yttrium, and plus scandium, are especially important for the high-tech and green-tech products. It should be noted. And this slide shows the principal use of rare earth elements. As you can see, the rare earth elements are strategic materials crucial for green energy technologies, novel electronic equipment, and aerospace instruments, and so on. And without these elements, every company cannot produce these high-tech and green-tech products. So the rare earth elements are very important for every country. Here is the example of the rare earth elements used for electric vehicle. This type of vehicle typically has 1 kilogram to 2 kilograms of iron neodymium boron magnet, which also contains 300 to 540 grams of neodymium, and also 80 grams to 144 grams of dysprosium. The dysprosium heavy rare earth element is very important for the magnet to work properly at the high temperature condition. And huge amounts of rare earth ores are needed for make this electric vehicle. So we can say HVs and EVs are a mass of rare earths. And more rare earth elements are needed for wind power generation. In a typical wind power generator has the 1.5 tons to 2 tons of iron neodymium boron magnets, which contains 450 kilograms to 600 kilograms of neodymium and 45 kilograms to 160 kilograms of dysprosium. So if we are going to construct much more wind power generation like this, very huge amounts of RE are needed in the future. Reflecting these tendencies, growing up the renewable energies or electrification of the vehicles, it is estimated that the global RE demand will increase rapidly and significantly. So, where can I get the huge amount of rare earth elements? This map shows the distribution of RE enrichment in the world. And you can see RE deposits are distributed all over the world. However, it should be noted that almost all deposits are of light rare earth elements. And so far, only iron adsorption type deposits in the southern China here exclusively produce heavy rare earth elements. And at present, more than 60% of rare earth elements produced by China. And of course, in case of heavy rare earth elements, almost 100% are produced by China. This results in an unstable market of the REE. This dominantly produced by one country. And there is another problem of the REE development. that is an environmental problem. For LRE type deposit, such as carbonatite and alkaline rock type deposits, these types of deposits are formed by magmatic activities. And during the magmatic processes, for example, the fractional crystallization, result in the enrichment of radioactive elements, sodium and uranium, together with rare earth elements, especially light rare earth elements. That's because the chemical behavior of the lanthanoids and actinoids are very similar during the magmatic process. And as a result, the enrichment of the sodium and the uranium causes a serious problem of the radioactive waste during the mining and smelting, especially at the countries Japan, Australia, and so on. And there is another problem for the HRE deposits. And this type of deposits, heavy rare earth element enrichment occurs in clay minerals formed by weathering of the granitic rocks, as shown in this figure. And HRE can be extracted easily by in situ leaching. What is the in situ leaching? The leaching acid directly injected into the outcrops of the deposits, then recovered the REE-enriched leaching solution like this. But of course, the significant part of the leaching solution cannot be recovered and flowing out to the rivers. This outflowing of the leaching acid causes a severe environmental pollution in the downstream area, as shown in this picture. So, the development of on-land RE deposits can cause environmental problems, and thus it seems difficult to build a sustainable future by much larger scale development of the on-land deposits. Here, against these backgrounds, we discovered a new rare earth element resource from the seabed that is called REE-rich med. Our discovery was published in the Nature Geoscience in 2011, and we found out that the deep sea sediments highly enriched in rare earth elements are distributed vast areas of the ocean floor of the Pacific Ocean. Our discovery was reported by major international news media, for example, Reuters, AFP, the Wall Street Journal, and BBC. These demonstrate that the REE, rare earth element, is quite important element for our society and economics. So far, 3 types of deep sea mineral deposits are known: hydrothermal sulfide deposits, cobalt-rich crust, and manganese nodule. And we discovered the 4th deep sea mineral resource of RE-rich med. The RE-rich med has many advantages as a mineral resource. The first one is a high RE content, especially heavy rare earth elements. As you can see, RE-rich med has a very good proportion of the RE content with 50% of heavy rare earth elements, including the yttrium, and another 50% of light rare earth elements. Even the iron adsorption type deposits in southern China have only 25% of heavy rare earth elements on average. So this is a good source of especially heavy rare earth elements. And the second one is enormous resource potential. At least 1,000 times larger than the world's current land reserves of REE exist on these two areas of the Pacific Ocean, around the Tahiti Island and around the Hawaii Islands. And third one is easy exploration. Because deep sea sediments are distributed continuously over the vast areas of the deep sea floor because of the very stable condition of the deep ocean. So we can take the information of the resource potential of the Lake mat, very scarce sampling, for example, the several hundreds kilometers apart, is enough. So, of course, we can take much more precise information by the dense sampling of the RE rich mat. Both cases, the sampling of the RE rich mat can be done by piston coring. The piston coring is the simplest way of obtaining the deep sea material. Just a metal pipe falls into the seafloor, then get the sediment samples. So we can get the RE rich mat samples very easily and cost effectively. That's the third point of the RE rich mat advantages. And the fourth one is easy leaching by dilute acid. Almost 100% of the REE are easily extracted from the mat to the diluted acid solution by the dilute acid and room temperature within 1 to 3 hours. So the final one is the most important one, low concentration of radioactive elements. As I said, the on-land RE deposits are characterized by the very high concentration of thorium and uranium. In contrast, the RE rich mat contain very low concentration of these radioactive elements comparable to average composition of the continental crust. So we can say RE rich mat is very clean resource. So this map showed the global distribution of the RE rich mat. And as you can see, the orange circle represents the RE rich mat. And the RE rich mat distributed vast areas of the Pacific Ocean, but we also detected the RE rich mat in the Indian Ocean and also Atlantic Ocean. However, the sampling is not enough so far, especially for the Atlantic Ocean and the Indian Ocean. So what controls of the distribution of the RE rich mat? In order to address this question, we conducted investigation using the statistical analysis on the dataset, geochemical dataset of the deep sea sediments. We use independent component analysis, ICA, applying to the geochemical dataset of the deep sea sediments. ICA is one of the signal processing techniques originally developed in the field of neuroscience and information science. And ICA can decode the original signals, for example, each sound of the instruments, and from the observed mixed data catched by mics by extracting non-Gaussian data structure. So we apply this method on the high-dimensional multi-element data of the deep sea sediment. As a result, we successfully extracted 3 key components for genesis of the RE-rich mat: manganese oxides from seawater, and calcium phosphates of biogenic origin, and iron oxyhydroxide from seafloor hydrothermal activity. All of these components concentrate rare earth elements by absorption of rare earth element in the seawater, especially under the condition of the very slow sedimentation. Based on the results, we revealed that the RE-rich mat is formed at deep sea basin, far from continents where sedimentation rate is very slow. Okay, next. After the discovery of the RE-rich mat in the Pacific Ocean, we also discovered the RE-rich mat within the Japanese exclusive economic zone, EEZ, around the Minami Torishima Island. Minami Torishima Island is a very small island, just 2 kilometers, 2 kilometers, and 2 kilometers. Yeah, it's much, much smaller than this big island of the Tenerife. And we successfully discovered the RE-rich mat in the Japanese EEZ around the Minami Torishima Island. And this discovery was also reported by both domestic and international news media. And this is Professor Yasuhiro Kato, a co-author of this presentation. And after the first discovery of the RE-rich mat in the Minami Torishima field, we conducted intense investigation, seafloor investigation, by collaborating with JAMSTEC, one of the National Institute for Ocean Science in Japan. So we finally discovered extremely RE-rich mat layer, which contains more than 7,000 ppm of the REE, that is 20 times higher than on-land deposits of the heavy rare earth elements in southern China. And we also revealed that the biogenic calcium phosphate, BCP, is the main host mineral of the rare earth elements in this RE-rich mat. And BCP is the fragments of fish bones and fish teeth, as shown in these photographs. And next, when did the extremely RE-rich mat form? Because I'm a geologist, so I was very interested in the timing of the formation of this high-grade ore in order to elucidate the ore genesis or formation mechanism of the RE-rich mat ore. So there are several methods to determine the depositional age, formation age of the deep sea sediments. For example, biogeostratigraphy, magnet stratigraphy, and radiometric age. Unfortunately, however, all of these methods cannot apply to the RE-rich mat. And finally, we found out that the only way to date the mat is osmium isotope stratigraphy. And based on the state-of-the-art analysis of the osmium isotopes, we successfully determined the formation age of the extremely RE-rich mat layer that is 34 million years ago. Yeah, that's a very old time. But very interestingly, the 34 million years ago is the critical age. The mode of global climate of Earth dramatically changed from the very warm greenhouse world to very cold icehouse world. And at that time, permanent Antarctic ice sheets started to expand greatly. And it is known that in the warmer period, the vertical circulation of the ocean was weak, and therefore dissolved nutrient salt such as phosphorus accumulated in deep ocean. At the time of onset of the global cooling, the circulation began strong. That's because sinking of the cold and dense seawater at the polar region. This results in the upwelling of the nutrient-rich deep sea seawater, and especially around the big seamounts, and increasing productivity of the surface ocean, including the fish activities. This in turn causes the increased supply of BCP on the seafloor and absorbing much more rare element from the sea water, resulting in the formation of the extremely RE-rich mud. So we can say global environmental change played an important role to produce the extremely RE-rich mud deposit, these interesting deposits. Based on the formation process we revealed, we can forecast the extremely rich mud is likely distributed near the foot of large seamounts in the deep sea basin. In case of Pacific, as you can see, red-colored areas. Of course, that includes the areas around the Minami Torishima Island. And we also investigate the resource potential of the REE in the Minami Torishima EZ. Based on the aerial survey of the Minami Torishima EZ, we targeted the promising area of the 2,500 square kilometers. And based on the huge amounts of geochemical data obtained from this promising area, we estimated and visualized the precise distribution of rare earth elements within the 10 meter below the seafloor. And finally, we found out the most promising area of the 100 square kilometers around here. Only the most promising area can produce 50 to 800 times of the Japanese annual RE demand and 1,800 times of the global annual supply of scandium. So RE-rich mud is a unique resource that can supply both huge amounts of heavy rare earth elements and scandium. And here I'd like to explain the importance of the scandium briefly. And the scandium is a member of rare earth element family, as I said. And industrial importance of scandium is rapidly and greatly increasing. For example, the aluminum scandium alloy that is a strong but light metal alloy, or high efficiency fuel cells, solid oxide fuel cells. So however, at present, global production of the scandium is very small, and that's very expensive. So, the early-rich mat contain high amount of scandium together with the rare elements, and importantly, the large portion of scandium can be extracted together with REE by dilute acid leaching. So, early-rich mat is also a good resource for this element, scandium. Okay, another important achievement of our research group is to find out a good way of increasing ore grade by using grain size separation. BCP is the most important host mineral for REE, as I said, and each BCP grain has 10 to 20,000 ppm of rare elements, or 1 to 2%. We found that the BCP grains are significantly coarser, bigger than the other grains of the mat, and therefore we can separate the coarser grained extremely RE-rich mat fraction from fine-grained non-RE-rich fraction by using grain size separation. Based on this result, we conducted experiments by using the hydrocyclone. That is a very simple way for the grain size separation. As a result shows that the grain size separation enables to improve the RE grade by 2.6 times and to reduce the mat volume to 20 to 50%. And this greatly improved the economics of the development of RE resource, RE rich mat. And next, I'd like to talk about the development system of RE-rich mat. These figures show the planned RE development system for RE-rich mat: floating, production, storage, and offloading system, FPSO. And this system is essentially based on the development system for deep sea oil. But difference, and the very important point, is the lifting system for lifting up the RE-rich mat. We are now planning to use the airlift system to lifting up the RE-rich mat by injecting the compressed air into the riser pipe. The RE-rich mat slowly becomes more buoyant than going up to the surface shape, then recover the RE-rich mat from the deep sea. And of course, in order to avoid the abnormal situation of the airlift system, such as slug flow or annular flow, which prevent proper lifting of the RE-rich mat slurry, we planning to inject compressed air at shallower portion and to take back pressure to rising flow. This significantly prevent the expand the injected air bubbles. Based on this concept, now our collaborating researcher in the University of Tokyo proceeds experiments on the airlift system for RE-rich mat, collaborating with several Japanese companies. And they constructed an airlift pump test system using a 200-meter vertical water tank at the Japanese Institute for Advanced Industrial Science and Technology, AIST, Japan. And they succeeded in pumping up slurries, simulating RE-rich math. And these photos show the recovered slurry here. It's a bit difficult to see. And the results show that the lifted flow rate of the math slurry was stable. That's a good sign, and does not depend on the viscosity of slurry. So, from the experiments, good results have been obtained for the application of the system to the development of RE-rich math. Okay, lastly, I'd like to explain the environmental issues with the RE-rich math development. In the pelagic condition, in the pelagic region, in the deep sea, there are only common species, probably no endemic species. This is quite different situation from the hydrothermal sulfide deposits, another types of deep sea mineral resource, where very dense organisms presented, and many of them are endemic for each hydrothermal bands. So, in case of developing the RE-rich math in a pelagic region, now we think that the ecosystem can recover after RE-rich math development. And another point is that the math itself is harmless, containing no harmful elements and materials. This is in contrast to the deep sea oils, methane hydrates, or hydrothermal sulfide deposits that are harmful for the organisms, including humans. And effective airlift system, as shown before, can inhibit spreading mud plumes into surrounding seawater. That's because just vacuuming the deep sea mud is enough, is doing for the RE-rich math development, mining. So we think that we can minimize the environmental impact of RE-rich math development on seafloor ecosystems. And also, I'd like to emphasize an important point of the environmental risks of resource development. And on-land deposits can be easily mined by anyone, which causes the illegal and unregulated mining. This results in the environmental pollution and human rights violations, such as child labor. These are going now. So this clearly, it's clear that this against the sustainable development of our society. In contrast, seafloor resources can be developed only by national agencies and or companies with high-level technologies and compliance. So, development of deep sea math is also in line with the direction of the SDGs and the international community. And now, the Japanese government started to progress the development of production technology for RE-rich math through the national project called Cross-Ministerial Strategic Innovation Promotion Program, SIP. And also, China and the United States are targeting RE-rich math now. And China has been conducting the exploration of RE-rich math in the Pacific and Indian Oceans, and now the results are published in many international papers, And also China got exploration mining license from the International Seabed Authority, ISA, at the very close region of the Minami Torishima EZ. Because these areas are one of the promising area for the extremely rich mud, we now think that China is also targeting the rich mud. And US also aims to develop the mud in the Pacific Ocean. United States deep sea mining company acquired an exploration right from the Cook Islands in 2016. And in this year, the company obtained a mining license of rich mud from the country. So, not only Japan, but China and the US, the superpower countries, are also moving toward the first development of rich mud. And this is the final slide. At present, a variety of advanced rich materials are used for high-tech and green-tech products, and some of more advanced RE materials may become commercial in several years. Furthermore, various new materials with RE are under study, as shown in many presentations in this conference. The development of RE-rich mud can supply huge amounts of RE in stable, which will greatly accelerate the application of the enhanced advanced RE materials in the various fields. I believe this will greatly, certainly open the way towards a sustainable future with RE-rich mud. Thank you for your attention.
Thank you, Professor Kentaro, for your very interesting talk that opens the way for the discussion today that will be very, very interesting, especially this afternoon in the round table at 5:30. So any question, José Luis?
Yeah, thank you. In that small triangular island, I think the advantage is that the mud is closer to the surface. Is it?
Yeah. This is a very flat.
What would be the depth?
Yeah, 1 or 2 meter depth.
Okay.
From the seafloor.
Another question, do you know any other mining? I mean, that compressed air sounds very interesting, but it's special for mud, I guess, right? Any other extracting options there are for mining? No mud, I mean in general.
Other than the rich mud, you mean?
Okay, thank you.
Sorry.
Thank you very much. Very, very interesting talk. My question has to do really with this slide. Because your deposit is very heavy rare earth rich, including lots of scandium, how dependent are the economics on developing uses for heavy rare earths? Because currently the economics for rare earths are being driven by the magnetic rare earth elements, right? Neodymium, praseodymium, dysprosium, and terbium.
You mean the economics of that? We perform the economic evaluation of this rich mud, and yeah, of course, the high concentration of the heavy rare earth element plus scandium is quite important to improve the economics of this rich mud. And we conducted economic evaluation, I haven't seen this presentation in a time limitation. We estimated the capex and opex, and then the evaluated the economics by using the discount cash flow. And finally, we obtained the result that shown in this figure. And this is a change of the RE price during the couple of decades. And the red line is the metal price required for RHMAT to become economically feasible. So NPV is going to plus. And as you can see, the RHMAT development is always economically feasible during the price range of the past 10 to 20 years. And also, this is NPV values of the.
We have time for one more question. Okay.
Thank you very much. Inspiring talk. I wish to know that it's easy to extract with acidic solution the component, but how easy and environmentally friendly is then to separate the different lanthanides?
Yeah, and we also are collaborating with the layers company and proved that the separation of each layer's elements can be done completely the same as the on-land RE deposits, product from the on-land RE deposits.
And is it environmentally friendly, or there is room for improving the, let's say, in this stage of separation? Mm-hmm. Is it impactful for the environment?
We only are using the leaching process, but the company doing the experiment of the separation process, and this is exactly the same as the method for the on-land RE deposits ongoing now.
Okay, yeah. Thank you.
Thank you for a very interesting talk. It's really nice to see how global cooling 34 million years ago can help us to combat global warming now by getting those very important elements out. My question is about, you identified this 105 square kilometer area, which is the richest in the rare earths, and that could supply 50 to 800 times the total use of rare earths in Japan. This is a factor of 15 difference. So what does this uncertainty come from? Because you really analyzed the content, so I would expect you knew exactly how much is in there.
How to analyze
And so if you go to the slide, you mentioned that in this 105 square kilometer area, that was enough for 50 to 800 times the total use of rare earths in Japan. But 50 or 800 is quite a difference.
Yeah.
So what does the uncertainty come from?
How to analyze the rares? I'm sorry, I've got the point. Well, sorry, what's the point? Shortly.
50 and 100 times. Why is different? This
50 times of what? Oh, yeah. Sorry, I got point. And this is depend on the current usage or current demand of the rares. That's because rares elements group of elements, many elements. So, but application is one by one for the one element to the one product. For example, neodymium, to the magnet.
Okay, so the uncertainty is in
Yeah, so
projected
the
use.
demand of each element of the rare earth is quite different. That's
Okay.
why the big difference
Okay, thank you.
between the.
For my totally ignorance on this topic, but I would like to know if you could help me to know if there has been also explorations, in other planets like the moon, satellites, because this is something that we for sure will have to see in the next years. I mean, like, we know that there is no planet B, and it seems that those rare earth elements are needed if we want to continue be the lifestyle we live. So do you know that if China on their spatial missions, the States, Russia has data on mass spectroscopy of the existence of such elements in the moon, which is the closest, let's say, satellite we have?
I'm not so familiar with the data from the other planets, including moon. And maybe there are some RE-rich rocks, but the advantage of the RE-rich mat and also heavy rare ores in the southern China is concentrate rare earth element by weathering process, aqueous process, not magmatic process. So that's why very easy to reaching from the ore to reaching solution. So in case of other planets, there is no weathering process, chemical weathering process occurred. So there is no this type of RE ores do not exist other than Earth, I think.
Thank you for this very interesting but also controversial presentation. I got a question but also I got a comment. My comment is that I would like remarking that not all on-land extraction of rare earths is done like it is done in China, because there are now already going on extraction in the United States, in Canada, and in Europe that is done under very strict environmental regulations. So I think that is important to be clarified. And then my question is, how long do you expect it will take before there is a large volume exploitation of these resources to be able to provide these materials to manufacturers, for example, of permanent magnets?
I think technologically it can be done by now. So we can supply or we can develop this kind of resource can be developed as soon as possible. But of course, even in Japan, the target of the rare earth is not only the exploring the new types of deposit, but also recycling or other processes getting the rare earth from the products. So it depends on the situation of economic or political situation of the rare earth. That is the same. I think that is the same of the Europe and United States also. So far I'm not so sure about the timing of the development of this kind of resource, new resource.
Okay, thank you. Just this round of questions makes me believe that this afternoon will be very, very interesting, the round table. So I just want to remind you this. So we stop now. Only a couple of announcements before. Tomorrow, you see in the doors, you can see a sign. Tomorrow, the closing session of the 3 plenary talks and the closing session will be in the other venue. Will be in the city center, Campus Central Paraninfo. It's the main historical building of the University of La Laguna. It's just a walking distance from the hotel. You'll see the maps if you go to the website, and you go /program. You see the maps here, the Google map. So we will meet you tomorrow at 9 at the Campus Central, okay? So thanks to the speaker again.
Thank you.